In the previous lecture, when dealing with step functions, there were some mistakes in the indices, sigma I equals 1 to n, aj, kij, etc. So I have corrected that in the lecture notes, and therefore I'm sure you will make sense out of it, and I'm sorry for that. Anyway, now we will continue. We will need to prove one more approximation result, for which we need a very important topological result on Rn. So we will start with that lemma. Every open set in Rn can be written as the disjoint countable disjoint union of half open boxes. So this is very important. You know, every open interval in R can witness a open set in R can witness a countable union of intervals. Similarly, every open set in Rn can witness a countable union of open boxes. Now we are saying you can write it as countable disjoint union of half open boxes. Okay, so proof n fixed positive integer. So let Fn denote the set of all points in Rn whose coordinates are all integral multiples of 2 power minus n. Okay, so you take Rn, let's take R2 for instance. So you take half, 1, 1 and a half, like that. So, and then here also. So draw lines at every half unit. So these points of intersection here, they are the F1. Now if you want F2, you have to further subdivide this each into 2. And so on. So you have 1 by quarter as the length of each box, and therefore you can so then you write Gn equals collection of all half open boxes with edge 2 power minus n and all vertices on Fn. So then the following two things are obvious. N fixed positive integer for every x in Rn, x belongs to exactly one box in Gn. That is clear, because Gn is the union of all these half open boxes. The boxes are disjoint, and Rn is the union of all these half open boxes. Boxes are disjoint, and therefore you have the, so when you say half open box, I mean something with these two is closed, the other two open, and so on. So secondly, let n be bigger than m if Q belongs to Gm and Q dash belongs to Gn, that means n is bigger than m, so Q dash has a smaller size than Q, then either Q dash is contained in Q or Q dash intersection Q will be empty, because you are subdividing each cube by 2 and therefore every new cube must be either a part of the old cube or it will be somewhere else, and therefore you have that these two are this. So these two are all obvious observations. So now let us continue the proof. Okay, so omega contained in Rn, open set. So up to now I only subdivided Rn into a grid of 1 by 2 power n size for every positive integer n. So if x belongs to omega, then there exists an open ball containing x contained in omega. Then for n sufficiently large, there exists a Q in Gn such that x belongs to Q contained in omega, because you have omega here and then x is here. Since the grid is sufficiently small when n is large, so certainly then x must fall inside some such box, and therefore you will have a cube like this. So in other words, omega is the union of all half open boxes contained in it and belonging to some Gn. Okay, so it doesn't matter. So this is a countable collection but may not be disjoint. So what we are going to do is the following. So now choose all boxes in omega belonging to G1, so they will all be disjoint anyway, and discard those boxes in Gk, k greater or equal to 2, contained inside this. So you are throwing away the superfluous ones. So now it's easy what you want to do. Now choose from the remaining boxes all those in G2 and discard those in Gk, k greater or equal to 3, contained in the selected boxes. So proceeding iteratively, omega is the union countable disjoint union of boxes from union Gn n. and this is obvious from the two observations which we made before. Okay, so you can always write every open set as a countable disjoint union of half open boxes. That is the moral of this lemma. So let us apply this. We will use this result repeatedly in a very important way later on. So now for the moment let us give an application using this thing. So let omega contained in Rn be an open set and E contained in omega, Mn of E finite. So it's a measurable set with finite measure. So when I say Mn of E, automatically I mean that the set is measurable. Then for every epsilon positive, there exists a set F which is a finite disjoint union of half open boxes such that Mn of E delta F, delta is a symmetric difference, is less than epsilon. They call E delta F is E minus F union F minus E. So given any set of finite measure, you can find a finite disjoint union of boxes such that the symmetric difference between these two is very small. So this is another approximation result. So you can approximate any measurable set of finite measure by means of half open boxes. Finite unions of half open boxes, which you must remember come from the original ring R. Okay. Proof. Let G contained in Rn open set such that E is contained in G and Mn of G minus E is less than epsilon by 2. So this we have already proved. This is one of the characterizations of measurable sets. Okay, so we have already proved this. So you know this. So you said G0 equals omega intersection G. Then G0 is also open because omega is open, and then E contained in G0, and then that is of course contained in omega because G0 itself is subset of omega, and then Mn of G0 minus E is also less than epsilon by 2 because it is G0 is contained in G, Mn of G minus E is less than epsilon by 2, and therefore G0 is. Now G0 is open, then G0 all have finite measure. Since E has finite measure, so we can, there exists Ij disjoint half open boxes such that G0 equals union J equals 1 to infinity Ij. And since the measures are all finite, so Mn of Ij sigma J equals 1 to infinity is finite. So choose K positive integer such that so you have a finite series, so the tail can be made as small as you can. So J equal to K plus 1 to infinity Mn of Ij is less than epsilon by 2. And now you define F equals sigma J equals 1 to K of Ij. So this is a finite disjoint union of half open boxes. And F is contained in G0. So Mn of F minus E is contained in Mn of G0 minus E, which we already know is less than epsilon by 2. And what is Mn of E minus F? E is contained in G0 again, and therefore E is contained in G0, and therefore Mn of G0 minus F, and that is equal to, in fact, sigma j equal to k plus 1 to infinity Mn of Ij, and that is less than epsilon by 2. So Mn of F minus E is less than epsilon by 2, Mn of E minus F is less than epsilon by 2, so Mn of E delta F is less than epsilon. So this completes the proof. Okay, so with this we complete the section on approximations. So next time we will take up a very important concept called translation invariance.